In the last video, you learned how to find the greatest common factor and the least common multiple using prime factorization. Just going to add a little bit of a twist here, and we're going to do a few examples with applications to greatest common factor and least common multiple. Example number 1. So we have the side length of the smallest, we're looking for the side length of the smallest square that could be tiled with rectangles that measure 16 centimeters by 40 centimeters. So you see I have a picture here. We've got a square, and we're looking to tile that with rectangles. And we want to have the smallest square that we could tile with rectangles that measure these specific dimensions of 16 by 40 centimeters. And we're also going to assume that the rectangles cannot be cut. So the key word here is smallest square. So we need the dimensions to be as small as possible. But we also need them to be the same because it's a square. So that's, in other words, we're just saying the least common multiple between 16 and 40. That will give us a square. So now the thinking part is done. Now we just go through the process that we did last video of finding the least common multiple between 16 and 40. So we're going to use the factor trees. I'm going to go through the factor trees and find the prime factors. So if you remember at this point, we now look at each unique factor, or each unique prime factor. So we have 2, and we take the one with the largest exponent. So that's the 2 to the exponent 4. And then the only other one we have is 5, and it's just there's no other 5, so we only take the 5. So then we have that 2 to the exponent of 4 is multiplied by 5 is equal to 16 times 5, which is equal to 80. So then let's return to the question. So we have context, so remember to answer the question. So if our least common multiple is 80, we've drawn this picture not quite accurately. So and I'll try my best here again. I'm not the most artistic. Okay, so just imagine that these are all equal rectangles. But you can see that we have 2 40s going down the side, which gives us 80 centimeters. And then along horizontally, we have 5 16s, which also give us 80 centimeters. So the side length, to answer the question of the smallest square that can be tiled by these rectangles, is 80 centimeters. Example number 2. So in this one, what is the side length of the largest square that could be used to tile a rectangle that measures 16 centimeters by 40 centimeters? So kind of looking at it from another perspective, we have a rectangle, and this time we're looking to tile it with squares. In this case, we're looking for the largest square that we could tile it with. So again, the key word here is largest. So we need to find the greatest common factor. So again, we are going to, well, we've already created the factor trees from the last one. So we're just going to revisit, rewrite our prime factorizations. So that's what we found in the previous question. And again, remember here, for greatest common factor, we are only interested in what's in common between the two. So the first one only has prime factors of 2, and it has 4 of them. The second one, for 80, has 3 2s, so we can only take 2 3s. Or sorry, 3 2s. So we take the 2 cubed, because we have 3 2s for 80, and we have 4 2s for 16. So we have 3 of them in common for both. And that's it. So the greatest common factor is equal to 8. So how does that look on the picture? And it looks something like that. So side length of the largest square that can be used to tile a rectangle that measures 16 by 40. So you can see we have 2 8s along the vertical, right? So 2 squares that go on top of one another, and then we have 5 squares horizontally, which gives us the 8 times 5, which gives us the 40 centimeters by 16 centimeters. So then we should write a sentence. And that's it.